Hi, all. This is Dr. David Branham. Welcome back. Today, I'll be doing chapter 6 of the textbook on reliability and validity in scale measurement. We'll just get started. As I will remind you, this is a supplementary video. It's not meant to replace your reading of the chapter. However, it is as comprehensive as I can make it, so it should help you a lot in doing well on the test. So let me share my screen and get going. The chapter 6, as I said, looks at scale, reliability, and validity. So we're going to look at scales, and we're going to determine the reliability and the validity of scales in this chapter. Note that the different types of validity are discussed in chapter 6 and in chapter 5. This chapter 6, looks at the validity of measurement procedures. Chapter 5 looked at the validity of your statistical tests. For instance, the internal validity of a experimental design and the empirical findings you find there, the external validity of being able to generalize your findings from sample to hot population. This chapter is different. It's looking at measurement and how valid those measurements are and how reliable those are. This chapter focuses only on reliability and validity of measures. Construct measure, the reliability and validity of construct measures. As you remember, constructs are what we use to measure our concepts that we have in our analysis. There are difficulties with measuring constructs in social science research. We've talked about those. Some variables are easy to measure, like a person's weight in pounds. However, measuring some important constructs is very difficult. For instance, how do we know whether we're measuring compassion or empathy? And since both constructs are somewhat similar in meaning, we need to first define what we mean by each of those. How do they differentiate? Or is it possible that they're actually the same thing? It's not adequate just to measure social science constructs using any scale that we prefer. We have to test these scales to ensure that, one, these scales indeed measure the unobservable construct that we want to measure. And that means that these scales would be valid. And two, that they measure the intended construct consistently and precisely. That would mean that these constructs are measured reliably. So that's the first difference we see in validity and reliability. A measure can be reliable but not valid if it is measuring something very consistently, but is consistently measuring the wrong construct. So you could be measuring something very well, but you're measuring something that isn't exactly what you're trying to measure. And in that situation, you have a reliable measure that's not valid. Likewise, a measure can be valid but not reliable if it's measuring the right construct, but not doing so in a consistent manner. Okay, for instance, if the easy one to look at here is weight. If you're on a scale and you weigh 120 pounds, and every time you get on that scale, it says you weigh 128 pounds, every time, you got a very reliable measure. It's measuring you at 128 pounds every time, even though you weigh exactly 120 pounds. The validity of the measure is off because you're not really measuring that weight. You're 8 pounds off every time. So that validity is off, but you're reliable in your measure because every single time it comes up 8 pounds over. Likewise, if you turn it around and you get on the scale and you average a weight of 120 when your weight is always 120, but you are randomly off, 115 one time, 125 the next, 113 off this time, 127 that time, your reliability is off, but you're measuring the construct correctly. It's just that you're not measuring it perfectly. So that's basically the difference between the two. Using an analogy of a shooting target, as was shown in figure 6.1 in your book, a multiple item measure of a construct is both reliable and valid with consistent shots that cluster within a narrow range near the center of the target. So if you look at that target there that says reliable and valid. So it's reliable because it's not too far off from the center of the target each time. It's only off just a little bit when it's off. It's valid because it is hitting the target you're trying to hit. So in that case, on that very first one, you have a reliable and a valid measure. On the second target, you have a valid measure because you are still measuring the center of the target. The problem is it's not that reliable. You have some randomness to it, and you're off pretty consistently, but you're not off in one direction or another. There's no bias there. You're just off. And so your reliability is down from the first one. Then go over to the third target. Here you have a reliable measure. It's still hitting right around the same spot every time. The problem is that you're not hitting your target. So it's not a valid measure of your target, even though it's very reliable in that it consistently is in the upper right-hand corner of that target. So you have an invalid measure on the last one, but you have a reliable measure on the last one. A measure that is valid but not reliable will consist of shots centered on the target, but not clustered within that narrow range, but rather scattered around the target, like number 2. A measure that's reliable but not valid will consist of shots clustered within that narrow range, but off from the target. Hence, the reliability and the validity are both needed to assure that adequate measurement of constructs of interest. You can't have one of them off and give you a good measure. Reliability, a lack of reliability means that your measure will be off. A lack of validity means that you're not measuring what you're actually trying to measure. Reliability. So let's get more specific on reliability. Reliability is the degree to which the measure of a construct is consistent or dependable. In other words, if we use this scale to measure the same construct multiple times, do we get pretty much the same result every time, assuming the underlying phenomena is not changing? Note that reliability implies consistency, but not accuracy. What are the sources of unreliable observations in social science measurements? For instance, an observer's subjectivity. An observer can be looking at something and coding a measurement, but can be off. Maybe not consistently off in the same direction. That would be a problem with validity. But the observer may be off just randomly around what he's actually or she's actually trying to measure. Different observers may infer different measures of morale, for instance, if they watch employees. On a very busy day, when they don't have time to joke or chat, employees may be very busy, and one observer may think, well, the morale is down because they're busy and they're not joking and chatting. Another observer will say the morale is up because they're working hard and they're not taking the time to joke or chat. So those are two observers that measuring the same thing, but a little bit differently. Then you might have a light day where there's a lot more jovial chat and talking and so forth. And that may change how the observer measures morale. Depending, also, it may depend on how they view the joke. Some people are insulted by some jokes and others laugh at them and think they're funny. That may change how you measure morale in that situation. So observers can be off and they can cause reliability problems. Sometimes reliability may be improved by using quantitative measures instead of observers, for instance, by counting the number of grievances filed over 1 month as a measure of morale. If you have more grievances, you have less morale. Grievances may or may not be a really valid measure of morale, but it is less subject to human subjectivity, and therefore that may be a more reliable type of measure. The problem may be that it's not actually measuring the concept of morale that you want to measure. It could be that they're, just looking at grievances by itself may be not a good measure of morale. A second source of unreliable observation is asking imprecise or ambiguous questions. This happens a lot in survey research, where you're asking a question and you're looking for an answer, but the question isn't understandable, or some people just have a hard time comprehending it. In those situations, you're going to have some unreliability in your measure. So how do you create these reliable measures? One, avoid ambiguous items in your measure. Don't try to be as simple and specific as you can be to make sure, especially when you're looking for respondents to answer your questions, make sure they understand that question so that they can give you a reliable answer. Simplifying the wording for your indicators so that they aren't misinterpreted by some respondents is a good way to make sure that you have better reliability. 4 ways of estimating reliability. Measurement instruments must be tested for reliability to see if they really are. And there's 4 ways that we're going to go over. Inter-rater reliability, retest reliability, split half reliability, and internal consistency reliability. The first one, inter-rater reliability, there's 2 ways to measure this. Inter-rater reliability is a measure of consistency between 2 or more independent raters or observers of the same construct. So people may be sitting there measuring the same construct independently. And what you want to do to see if you want strong reliability, those 2 raters should be rating each indicator the same way. So if a measure is categorical, for instance, an either or measure, yes, they're doing this, or no, they're not. A set of categories is defined, and then the raters check off with each category where the observation falls in. And the percentage of agreement between those raters is an estimate of inter-rater reliability. For instance, if 2 raters rate 100 observations into one of 3 possible categories, and their ratings match for 75%, the inter-rater reliability score would be 0.75. It's a pretty simple way to do it. If the measure is an interval scale or a continuous scale, for instance, a 1 to 7 scale, then you simply correlate the responses of the 2 raters. And you can see that the inter-rater reliability from the correlation coefficient. If one person says 6 and then this person says 5 when they're measuring the same thing, and then the next indicator comes up and they're measuring 1 and 1, you got pretty consistent reliability there. And you can just correlate those pairs to see what your measure would be. Then you have something called test-retest reliability. And test-retest reliability is a measure of consistency between 2 measurements, like tests, of the same construct, administered to the same sample at 2 different points in time. So if the observations have not changed substantially between the 2 tests, then the measure is reliable. So you're basically given one test, seeing, for instance, if you want to measure intelligence, you give an intelligence test here, you can take it back and then wait some time and give the same intelligence test over again. If those 2 scores are very close between tests, then you have a lot of test-retest reliability. If the scores are further apart, there's less reliability. The correlation in the observations between the 2 tests is an estimate of the test-retest reliability. So if you have a person who makes an 84 on one test, then they come back and take the same test later and still make an 84, that's very strong reliability. And if everybody does that, where they make the same exact score each time, then you'll have a reliability score of 1, which is perfect test-retest reliability. However, we should note that the important thing in this test-retest reliability is almost always how quickly you retest. If you take a long time before you retest, then that reliability always goes down. So if you want high reliability scores, you'll do that test and then that retest very close together. Now, split half reliability is pretty close to the same thing. It's just that split half reliability is a measure of the consistency between 2 halves of a measure. For instance, if you're measuring intelligence, you might split the test in half. And then if you have a 10-item measure, for instance, for a given construct, you randomly split those questions into two tests. And so You give one test, but then you randomly split them into two tests. And the expectation is that those two scores should be the same if you have a reliable test. So you randomly split the 10 items into 2 5s, then calculate the total score of each half for each respondent. And the correlation between the two total scores in each half would be a measure of your reliability. You would want, if you want a highly reliable test for, say, intelligence, you would give a 100-question test. You randomly split the questions 50-50, where you basically flip a coin on each question and say, okay, it's in this one, next one's in this one, and so forth. And then you would expect that those scores would be the same for each test if you have a reliable test. Then the last one we're going to talk about is the internal consistency reliability. Now, this is a little bit more complex. Internal consistency reliability is a measure of consistency between different items of the same construct. So if you have a multiple item construct measure, multiple items, I mean, for instance, measuring intelligence, you have multiple questions. So the extent to which the respondents rate those items in the same manner then is a reflection of the internal consistency of the test. This makes the assumption that each question is about the same as far as ability to measure the concept. This is a problem. I personally have a problem with how you do this, where you're making this assumption that every indicator has the same power and is measuring the same exact thing, because concepts sometimes can be complex. They can have more than one indicator that will measure them in a proper way. So this is an assumption that we make, but I criticize it here, but I've used this. I use this Chromebox Alpha and what we're about to talk about, principal components factor analysis. I used it in my dissertation when I was getting my doctorate degree. I used it in the last article that I published. So it's not unusual to do this. It's a good way to see if you are, especially if your indicators are supposed to be measuring the same thing, to see how consistently they're measuring that. So, for example, with Chromebox Alpha, if you have a scale of 6 items, you will have 15 different pairs, and the correlations between those the pairs of those items would be your score on the Chromebox Alpha. So then we go to validity, which is different from reliability. We measure reliability 4 different ways. So validity is different. We know that it's different in that, valid measures are ones that are actually measuring what you want to measure. That's important. It's a reminder now. I want to remind you that these are different types of validity discussed here than we did in the previous chapter. Remember that chapter 5 covers the validity of hypothesis testing procedures, internal validity being, empirical analysis at the experimental design. That is the highest internal validity that you can have because it establishes causation better than any other statistical measure. External validity, the ability to generalize to the population. That's what we covered in chapter 5. This covers the validity of your measures. And so let's make sure we don't get that mixed up, especially on the test. On the test, I'll label it chapter 5 and chapter 6 on each question. So you should be able to distinguish when you see that first part of the question. Construct validity, the validity of measures. Okay, validity of measures, often called construct validity, refers to the extent to which a measure adequately represents the underlying construct that it's supposed to measure. For instance, it is a measure of compassion, really measuring compassion, and not measuring a different construct such as empathy. Is compassion and empathy, are they different? And if they are different, how are they different? And when we go to measure them, how do we measure them differently and decide that we are measuring exactly what we're trying to measure? So validity can be assessed using theoretical or empirical approaches and should ideally be measured using both approaches. Theoretical approaches basically say, okay, theoretically, this is how I would measure something, and you put it down. When you do that, it's best to have individual input from other experts, if you can. Most of the time, in all honesty, you don't have that unless you're doing a research proposal that, that some funding think tank, for instance, is trying to determine whether you're actually measuring what you want to measure. In that case, you might have a group of people scrutinizing your measure to see if you're actually measuring what you say you're measuring. Most cases, that's not the case. You have to do this yourself. But when you go to publish, in almost every case, you'll have reviewers who will scrutinize these measures as well. So theoretical assessment of your validity of your measures, it's helpful to have. Most of the time you want to go to somebody who's doing these measures and is an expert at doing these types of measures and get their opinion. Maybe they can help you do this better. On the other side, there's empirical approaches, ways to measure whether you're measuring that same construct. And if that construct that you're measuring is accurately being measured, there are some tests. I already mentioned one, the principal components factor analysis. Ideally, you should use both of these approaches, theoretical and empirical, when measuring validity. Theoretical assessment of validity. Theoretical assessment of validity, as I just discussed on the previous slide, focuses on how well the idea of a theoretical construct is translated into or represented in an operational measure. In other words, how well are you measuring the construct? If your construct is empathy, how well is your measure actually measuring empathy? This type of validity is called translational validity or representational validity. And it consists of two subtypes. One is face validity. When I look at this, does it look like you're measuring what you're trying to measure? A lot of times with empirical analysis of validity, you're not getting that face validity. Your test may say, this is what I'm measuring, but when you read it, when people who in the know read this, they're going, nah, I don't think so. This doesn't sound like you're actually trying to measure what you say you're trying to measure. So, it's important that on the face, there's some believability in your measures of your construct. Then there's content validity. Translational validity is typically assessed using a panel of expert judges who usually use face validity, who rate each item or indicator on how well they fit the conceptual definition of the construct. That means, one, you're going to have to define your construct. You have to define what your construct is. If your construct is empathy, you have to define empathy. This is what it is. The experts will say, is this really a definition of empathy? And then once you define it, they'll look at your measure. Is he or she actually measuring that empathy that they defined? Face validity, as I talked about before, refers to whether an indicator seems to be reasonably measuring its underlying construct on its face. Excuse me. For example, the frequency of one's attendance at religious services seems to make sense as an indicator of a person's religiosity without a lot of explanation. So if a person is religious, they tend to go to a lot of religious services. So you can count up the times they go to a religious service, and that would be a pretty good measure of their religiosity. It has face validity. I can see that. It seems like it makes sense. If your research includes constructs that are highly abstract or constructs that are hard to conceptually separate from each other, like compassion and empathy, it may be worthwhile to consider using a panel of experts to evaluate the face value of your construct measures. If you don't have a panel of experts, go individually. If you're in a university, you can go into a department and go to people who've done this types of research before. If you go to a conference, it's a great way to do it, to make a conference presentation and get some input from people who are experts. For instance, somebody who is reviewing your paper at the at the conference, to tell if your construct is really measuring what you think it should be measured. Face validity is one of the first things they'll look at. Then there's content validity. Content validity is an assessment of how well a set of scale items matches with the relevant content domain of the construct that it's trying to measure. Now, as I said, I have issues with this because sometimes the construct that you're trying to measure has different aspects to it, where questions might be trying to measure one aspect, and then a different question is trying to measure a different aspect. If you do that, there will be an inconsistency in your measures. So this assumes that every indicator that you're using to measure that construct has the same measure in mind. It completely measures the construct. And then you have 3 or 4 different measures that completely measure that construct. And if they are correlated, if they're the same, then it looks like that your indicators are actually measuring the construct you're trying to measure. An example, if you want to measure the construct satisfaction with restaurant service, you might look at the quality of food, the courtesy of the wait staff, duration of the wait before getting your food, or the overall ambiance of the restaurant. This content validity would assume that these would be correlated. My issue is that sometimes they're not correlated. Sometimes the quality of the food is fantastic. The wait staff isn't. And you still go to the restaurant anyway because you just want the great food. So yes, I think most times content validity is valid in that when you have a single measure, you are measuring what you want to measure. But if you're looking at different aspects, like a restaurant quality has a lot of different components to it. So when you do a principal components factor analysis, like we're about to recover, you're going to find some lack of correlation. And that these measures, this measure, courtesy of the wait staff, is not the end all be all of that restaurant. The quality of the food may be great, the wait staff may be lousy, and that lousy wait staff and the high quality of food will not correlate with each other. This approach requires a detailed description of the entire content domain of a construct, and it means that your indicators need to measure that domain. And it may be difficult for complex constructs like I'm talking about, such as self-esteem or intelligence. How do you measure intelligence where every single indicator should correlate with each other? There are different types of intelligence. So some people may be highly intelligent in one area and not on the other. If that's the case, the indicators on those two indicators will not correlate with each other. So empirical assessment of validity, empirical assessment of validity, that orange box that we have there, examines how well a given measure relates to one or more external criteria based on empirical observations. And so if you go from there to the arrow that goes to the gray box, this type of validity is called criterion-related validity, which includes 4 subtypes: convergent validity, discriminant validity, concurrent validity, and predictive validity. So we'll cover all 4 of these. Criterion-related validity examines whether a given measure behaves the way it should, given the theory of that construct. This assessment is based on quantitative analysis of observed data using statistical techniques such as correlation analysis, factor analysis, and so forth. So, empirical assessment of, we're continuing with empirical assessment of validity. The 2 types, the first 2 on our list were convergent validity and discriminant validity. Now, these 2 are directly related to each other, so we're going to cover them at the same time, just as your book does. Convergent validity refers to the closeness with which a measure relates to or converges on the construct that it's purported to measure. And this goes right to the example I had before, where intelligence questions that measure intelligence are assumed to be correlated with each other. One measure of intelligence, and if a person can answer that correctly, they're expected to answer the next one correctly. If a person can't answer the first one correctly, they're expected to have less success on the second one. There's supposed to be a correlation between these items that measure intelligence. So that's convergent validity, where each indicator should correlate in success with the other indicator. Convergent validity can be established by comparing the observed values of one indicator of one construct with that of the other indicators of the same construct. the intelligence questions. One question would be one indicator, the rest of the questions would be the other indicators. So when you compare that and demonstrate that there's similarity or a high correlation between the values of those indicators. So that's convergent validity. All these indicators should be correlated with each other. An intelligent person who knows the answer to this will know the answer to this, who will know the answer to this. A less intelligent person who doesn't know the answer to this will probably not know the answer to this either, and so forth. Discriminant validity refers to the degree to which a measure does not measure or discriminates from other constructs that it's not supposed to measure. So discriminant validity is established by demonstrating that indicators of one construct are not the same or dissimilar, have a low correlation with other constructs. So they're actually kind of one and the same, and that they're polar opposites. So convergent validity says these measures of the same construct will have success in correlational success. Discriminant validity says if these aren't the same, they won't have correlational success, which means that in a way they're measuring the same thing. Exploratory factor analysis is a way to measure both of these. So exploratory factor analysis, which we won't be doing that in this class, but you could be doing it later in a statistics class. Probably not undergraduate statistics, but when you get to grad school, exploratory factor analysis is something that you may do. Exploratory factor analysis is a method used to calculate convergent and discriminant validity. Exploratory factor analysis uses bivariate correlation between your indicators. It looks at each indicators and sees how much they correlate with the answers on the other ones. Let's take intelligence. If you have 3 indicators there that say this is what I'm measuring for, these are indicators of intelligence. A person who answers one will probably answer correctly on the next one and correctly on the next one. And so that correlation will give you a high factor score. So if you have that high factor score here, factor loadings of above 0.6, you have those, they're telling you that you're measuring the same thing, that you have convergent validity here. So there over here, there's an example, a principal components factor analysis over here. If you have a 0.6 or higher score, it's probably, and they all load on one factor, that those factors are basically measuring the same concept. So factor 1 is measuring the same concept. It could be that KL1, KL2, and KL3 are all measuring intelligence. And you have 3 different questions there. If a person can answer all 3, that means they're highly intelligent. The correlation between being able to answer one and being able to answer the other one is very high. If a person can answer 1, they probably can answer 2 and can probably answer 3 too. The correlations in PF1, PF2, and PF3 indicate they're measuring something else altogether. It's not intelligence. It may be something else, but there is another factor, factor 2, that has high factor loadings. So you actually are measuring 2 separate constructs with this factor analysis. And you can filter those out and say, okay, these are 2 constructs. They may be the empathy and compassion. Factor 1 may be empathy, factor 2 may be compassion. The discriminant analysis in the white blocks is saying you're not measuring this, but you're measuring it here, but you're not measuring it there. So exploratory factor analysis uses the bivariate correlation between indicators of a construct to filter out which indicators are measuring a construct and which indicators are measuring a different construct. So you have 2 constructs in this factor analysis. If the only thing you were trying to measure was intelligence, and you got a factor analysis that had 1 factor with all the components over 0.6, it would be a very good sign that you are doing a very good job of measuring intelligence, and you can get a factor score to measure the intelligence. But in this case, we have a factor 2 here that's telling us we are measuring something completely different with PF1 and PF2 and PF3 than we're measuring with KL1, KL2, and KL3. And that means we got 2 separate constructs here. So it could be intelligence. It could be the factor 1 is quantitative intelligence, and factor 2 is logical intelligence. It could be that. And that would make a lot of sense, that you're measuring two different types of intelligence with this factor analysis. So you have to basically understand, one, you look at your indicators and say, this is the construct I'm measuring with these indicators. Do they correlate? Yes, well, on factor one, so I am measuring that. On factor two, they measure very well on PF1, PF2, and PF3. So I have a different construct there. It may be something, they may be related, but they're two completely different measurements of constructs. For adequate convergent validity, it's expected items belonging to a common construct should have factor loadings of 0.6 or higher. So because factor one has factor loadings of 0.6 or higher on KL1, KL2, and KL3, then there's convergent validity that factor one is measuring the construct it's meant to measure. The same is true for factor two on PF1, PF2, and PF3. Okay, a single factor should have 0.6 or higher on each of the loadings. While for discriminant validity, those items should have factor loadings of 0.3 or less. So if you have a 0.3 or less, like PF1, PF2, and PF3 have on factor one, they're basically saying with discriminant validity that you are not measuring the concept that you say you're measuring with these. And the same is true on factor two with KL1, KL2, and KL3. So if using my previous example, if factor one is mathematical intelligence, then we know that these three are actually measuring mathematical intelligence. We have convergent validity that they are doing so. And then PF1, PF2, and PF3 are not measuring mathematical intelligence. We have discriminant validity evidence that that's the case. On factor two, the logical intelligence, we know that KL1, KL2, and KL3 are not measuring logical intelligence. That's discriminant validity. They all have scores of 0.3 or less. But PF1, PF2, and PF3 all have factor loadings of above 0.6. So they are measuring logical intelligence, and that is convergent validity that they are measuring it. So that's how exploratory factor analysis works. It's a good tool. Some people have low opinions of it, especially in economic analysis. Political science doesn't use it nearly as much. Psychologists use it a whole lot. It's a psychometric measure. So, I would say use it when needed. If it's a tool that you need, I've used it in my career on some occasions. So if it's a tool that you need, just use that. Continue on with the other two types of validity. Predictive validity is the degree to which a measure successfully predicts a future outcome that is theoretically expected to predict. For instance, your SAT scores should be predicting future college success. It's a standardized test to measure future college success. So it does, I think SAT scores give you a good measure of academic intelligence, in that you could have learned your academic intelligence, or you may be gifted intellectually where you can do it. But it does show that you have the tools to be successful in college. But SAT scores, for instance, they're valid in that they do predict. If you make a high SAT score, you have a lot better chance of being successful in college than if you don't. But we have error in that. And a lot of the error is simple. It could be that the high school you went to didn't prepare you well, even though you're highly intelligent and you're very driven. SAT scores don't tell you how driven you are. So there's always examples. This is what I always want to make sure people know. There's always examples of people who have overcome the prediction and done very well, even though they were predicted to not do well. And there's a lot of examples of people who are predicted to do very well who don't do well at all, because there's other factors involved. I think the SAT test has a pretty good measure of your intellectual and academic ability to enter college and be successful. Pretty good measure, but it could be overcome. You may be able to take some entry classes, get yourself up to that level. But it isn't a measure of academic drive. of motivation. I don't think it measures that at all. There are a lot of very intelligent people who never get a college degree because they're just not motivated to do that. So predictive validity, understand, it's the degree to which a measure really predicts what it's supposed to predict in a future outcome. Concurrent validity examines how well one measure relates to another concrete criterion that it is presumed to occur simultaneously. For example, do students' scores in a calculus class correlate well with the students' scores in a linear algebra class? The thought is that success in these take the same skill. So if you have scores in a calculus class, you're assumed that those algebra scores will be good as well. In most cases, this is true in real life. People who do well in calculus have usually done well in algebra before. These scores should be related concurrently. So if you have concurrent validity in that you do well in one, then you should do well in the other, then that's what you have. So a good prediction of success in calculus may be how well you did in your algebra class. That makes sense. Although there are different skills in calculus than there are in algebra. So it's not a perfect way to validate a measure, but it does have concurrent validity in that there is a correlation between those two. Theoretical and empirical assessment of validity. This distinction between theoretical and empirical assessment of validity is illustrated in figure 6.2 in your book. However, both approaches are needed to adequately ensure validity of measures in social science research. And even with both approaches, it's very difficult to assure that you have validity on both sides. That theoretical validity, do you have face validity? Is there content validity? Do our experts say that it looks right? That theoretical validity is important, but the statistical analysis is also very important. It's a good idea to run these tests to make sure you have this type of validity. So both approaches are important. And lastly, we're going to talk about, and this is basically related to everything we've done in this chapter, is random error and systematic error. And it goes to reliability and validity. Random error is the error that can be attributed to a set of unknown, uncontrollable external factors that randomly influence some observations, but not others. Such error will reduce the accuracy of your measure, but it won't cause bias. A classic example of this are these targets. Remember these previous targets where the first target down on the bottom left side is both accurate and it's also hitting the target. It's hitting the target, so it's valid. It's accurate in that it's reliable. But if you have these non-systematic errors where you just random things are causing a target to be missed, and that you're having some error in where you can't really tell by a score whether or not you're right on or not. You have some variability, that goes on that's random. It just means that you are measuring what you're trying to measure, but you're just not doing it with a lot of accuracy. That's a random error. Systematic error, random error is in the second target there. Systematic error is an error that is introduced by factors that systematically affect all observations of a construct across an entire sample, and it's in a systematic manner. This is done in that right-hand target where you see all the dots that are to the right and above the intended target. We have a systematic error here. We have a very reliable error, but it is systematic. Systematic error is sometimes considered to be biased. For instance, if you're shooting arrows and this is what you're doing, you're a very good shot, but you have something that's causing a bias because your shot is very reliable, but perhaps you have a wind that's moving up and to the right that's moving all of your arrows up out of the target area. That's a bias in your measurement, and it should be corrected because it can cause erroneous research outcomes. So among these two, it's important to understand that one is worse than the other. So random and systematic error implications for measurement procedures. When you have random error, it increases the variability of the observation. So you don't have this first target over here where they're all together. There's very low variability in those observations. That second target that says valid but not reliable, there's a lot of variability in the observations, but there is no bias. I mean, it's hitting there. And when that happens, when you have random error, it reduces the reliability of your measure, but it's still a viable measure. It's better to have something that measures with a loss of reliability than no measure at all. So in most cases, we do have a loss of reliability in our errors. And so when you have this, yes, for instance, when you go to statistics, your t-scores will go down because you have this high variance. Your t-scores will go down. It'll be harder to get statistical significance, but it's still a good measure, and you still may be able to make a finding. In contrast, by shifting the central tendency measure, like you do in the last target, that says reliable but not valid, you have systematic error that reduces the validity of your measurement. And this validity concerns are far more serious problems than when you have reliability concerns, because an invalid measure is probably measuring a different construct than what we're intending. So you're not measuring a construct that says I'm shooting the arrow to the target, and so I'm measuring that construct by shooting these arrows at the target. You're measuring a construct where you're shooting arrows at the target with a wind that's going up and to the right. And that's a completely different construct than what you intended to measure in the first place. An invalid measure is probably measuring a different construct than what we intended, and hence validity problems cast serious doubts on the findings derived from a statistical analysis. You need to avoid validity at all costs, loss of validity at all costs. You need to have valid measures. You do need to reduce the reliability errors that you have, but sometimes you can't do that. And that doesn't mean you throw out the baby with the bathwater. An unreliable measure is okay. It's just not going to give you that statistical power that you need. Okay, thank you very much for the video. I hope this helps you. I think it will help you. As I want to remind you, if you have any questions, let me know. Shoot me an email. We can do a Zoom meeting. We can do a telephone call, or we can just do it by email if you want, just depending on what you have. Have a good day. I think this is going to help you a lot with your test. I wish you well.